What's up? I'm going to teach you guys how to determine the convergence of a series in n. Let's start here. Nth term test. With the nth term test, all you have to do is ask yourself, does the limit as n approaches infinity of a sub n equal 0? If your answer is no, then this series is divergent. Here's an example.
Here are some examples for the nth term test. For our first example, we have the summation from 1 to infinity of n over n plus 1. Since the limit as n goes to infinity of n over n plus 1 equals 1 and not 0, our series is divergent.
If your answer is yes, then this. This is inconclusive.
For the second example, we have the summation from 1 to infinity of 1 over n squared. Since the limit as n goes to infinity of 1 over n squared equals 0, the nth term test is inconclusive.
This is inconclusive. You have to try this. Geometric series test. If your series is of this form, then you can have one of two possible options. If the absolute value of your common ratio, r, is less than 1, then your series is convergent by the geometric series test. However, if it is the opposite case and is greater than or equal to 1, then your geometric series is going to be divergent by the geometric series test.
Examples for the geometric series test. For the first example, we have the summation from 1 to infinity of 5/4 to n. Since r is equal to 5/4 and the absolute value of 5/4 is greater than 1, our series is divergent. For the second example, it's another geometric series where r equals -2/3. Since the absolute value of -2/3 is less than 1, our series is convergent. For the final example, this is not a geometric series, so the geometric series test does not help.
A geometric series of this form, then you're going to have to try this test. Series test. If your series is of this form, then you have one of two possible outcomes. P is less than or equal to 1, then your series is divergent by the p-series test. If your p is greater than 1, then your series is convergent by the p-series test.
Some examples for the p-series test. For the first example, summation from 1 to infinity of 1 over n to the 1/2, p is equal to 1/2. Since 1/2 is less than 1, our series is divergent. For the second example, it is also a p-series with p equal to 3. Since 3 is greater than 1, the series is convergent. For the final example, this is not a p-series, so the p-series test does not help.
This is not in the form of p-series, try this. Positive term test. The positive term tests require that you test the absolute value of the series because, of course, as the name implies, they only work with positive terms. Remember, if the absolute value of your series is convergent, then your series is absolutely convergent. So let's look at the 4 absolute value tests. So the first one you're going to try is the integral test. If f, which is your function here, is positive and decreasing for all x values greater than or equal to k, and a sub n is equal to f of n, then you're going to set up your series and compare it to an integral from k to infinity. If the integral from k to infinity comes out as a finite number, meaning it converges, then both of the things are going to converge. However, if it comes out as infinity or negative infinity, then they're both going to diverge.
Some examples for the integral test. For our first example, we have the summation from 1 to infinity of 1 over n. We can use the integral from 1 to infinity of 1 over x dx to determine the series convergence or divergence. Since the integral diverges to infinity, the series is also divergent. For the next example, we have the summation from 1 to infinity of 1 over n squared. We can use the integral from 1 to infinity of 1 over x squared dx to determine the series convergence or divergence. Since the integral converges to 1, the series is also convergent.
What you're going to try is the ratio test. And the ratio test asks if the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, what does that come out as? If the result is less than 1, then your series is going to be convergent by the ratio test. If it's greater than 1, then it's going to be divergent by the ratio test. If it is equal to 1, the test is inconclusive and you're going to have to try something else.
Examples for the ratio test. For our first example, we have the series of 3 to the n over 5 to the n plus 1. From this series, we can find a sub n and a sub n plus 1 and find the limit as n goes to infinity of a sub n plus 1 over a sub n. Since this limit equals 3/5 and 3/5 is less than 1, the series is convergent. For our next example, we have the series of n times 3/2 to the n. From this series, we can find a sub n and a sub n plus 1 and the limit as n goes to infinity of a sub n plus 1 over a sub n. Since the limit equals 3/2 and 3/2 is greater than 1, the series is divergent.
This test you're going to try is one of the comparison tests. The first one we're going to look at is the limit comparison test, which asks, as the limit of n, as n approaches infinity of a sub n over c sub n, what does that come out as? If it's equal to a positive finite number, then either both are going to converge or diverge. If it comes out as 0 and c sub n converges, then a sub n also converges, and if it comes out as infinity and c sub n diverges, then a sub n also diverges.
Here are some examples of the limit comparison test. For the first example, our series is n to the 1/2 over n squared plus 1, and we use a comparison series that is convergent. We take the limit as n goes to infinity of n to the 1/2 over n squared plus 1, our series term, divided by the comparison series term. Since this limit equals 1, which is a finite number, our series is also convergent. For the next example, our series is the summation from 1 to infinity of 1 over natural log of n. We compare it to a divergent series, 1 over n. Since the limit of our series divided by the comparison series equals infinity, our series is also divergent. For the final example, our series is e to the negative n squared. We use a comparison series that is convergent. Since the limit as n goes to infinity of our series over the comparison series equals 0, our series is also convergent. Here are some examples of the direct comparison test. For our first example, our series is sine of n over n squared. We use a comparison series, the summation from 1 to infinity of 1 over n squared, which is convergent, and since sine of n over n squared is less than or equal to 1 over n squared for all n greater than or equal to 1, our series is also convergent. For the next example, we have our series is a summation from 2 to infinity of 1 over the natural log of n. We use a comparison series that is divergent, 1 over n, and since our series is greater than or equal to the comparison series for all n greater than or equal to 2, our series is also divergent.
Alternating series test states that if the terms alternate and decrease in magnitude to 0, then the series will be convergent every single time. If none of these work, sorry, you're completely out of luck.
Here's an example of the alternating series test. This example, the summation from 1 to infinity of negative 1 to the n over n, meets the 3 requirements for an alternating series. The terms alternate in sign, decrease in magnitude, and go to 0. So the series is convergent by the alternating series test.